Hello, everyone, and welcome to the stream. I'm Jared. You can call me Jardo if you want. And we are working on Advent of Code puzzles in Ruby, specifically the 9th day. And we will be, I don't know what we're doing yet. I haven't looked at the puzzle, going into it yet again, blind. So let's see what happens here. Actually, here, let's just finish getting set up here. We'll copy over our template and touch day9.txt. I'm on a different keyboard today. Should be slightly less noisy. The keyboard I regularly use, I was getting some double fires on my space bar. It's not a space bar, my space key. My keyboard looks like this. There we go. But fortunately I have two of them, different switches in them. So we just swapped over to the other one. And let's see what day 9 has for us. Another push of the button leaves you in the familiar hallways of some friendly amphipods. What's an amphipod? Amphipod. Shrimpy looking guys. Okay. Good thing you each somehow got your own personal mini submarine. The historian's jet is in search of the chief, mostly by driving directly into walls. Okay. While the historians quickly figure out how to pilot these things, you notice an amphipod in the corner struggling with his computer. He's trying to make more contiguous free space by compacting all of the files, but his program isn't working. You offer your help. He shows you the disk map, your puzzle input, he's already generated. For example, and then we're given a input, and let's just take a look at this one. Well, it is one that could conceivably parse as Ruby, but I don't think we could solve it with eval. The first example above represents these individual blocks. 0, 0, dot, 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 1, 1, 1, dot, 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 2. Sorry, I skipped ahead. Whoops. The disk map uses a dense format to represent the layout of files and free space on the disk. The digits alternate between indicating the length of a file and the length of free space. So a disk map like 1, 2, 3, 4, 5 would represent one block file, 2 blocks of free space, and a 3-block file, 4 blocks of free space, and then a 5-block file. Disk map like 90909 would represent 3 9-block files in a row with no free space between them. Each file on disk also has an ID number based on the order of the files as they appear before they are rearranged, starting with ID 0. So the disk map 1, 2, 3, 4, 5 has 3 files, a 1-block file with ID 0, a 3-block file with ID 1, and a 5-block file with ID 2. Using one character for each block, where digits are the file ID and dot is a free space, the disk map 1, 2, 3, 4, 5 represents these individual blocks, 0, 1, 1, 1, 2, 2, 2, 2. Thank you, Fig. It was getting difficult to follow by the end, and I'm glad that it didn't get too complex for us to complete doing that route. The example above, 2, 3, 3, 3, 1, 3, 3, 1, 2, 1, 4, 1, 4, 1, 3, 1, 4, 0, 2 represents these individual blocks. That makes sense to me. The amphipod would like to move file blocks one at a time from the end of the disk to the leftmost free space block until there are no gaps remaining between file blocks. For the disk map 1, 2, 3, 4, 5, the process looks like this. The first example requires a few more steps, so 9, 9 is then moved to move file blocks one, but this isn't moving the entire, it is moving the entire block. Isn't this a block though? Or is... Oh, no. Blocks are the individual pieces. Okay. And so 8, 8 is going to get part. Okay. I wouldn't be surprised if the final step was to move them into contiguous chunks. But we won't worry about that. The final step of this file compacting process is to update the file system checksum. To calculate the checksum, add up the result of multiplying each of these blocks' positions with the file ID number it contains. The leftmost block is on position 0. If the block contains free space, skip it instead. Continuing the first example, the first few blocks positions multiplied by its file ID 00, etc. Compact the amphipod's hard drive using using the process he requested. What is the resulting file system checksum? Be careful copy pasting the input for this puzzle. It is a single very long line. Yes, it is. All right, so pop that in there. Good, we've got a single very long line. We can just strip that, and I think cool. Yeah. Alrighty. Can I just check that you're happy with the word hints? With it? Oh yeah, hints are fine. We're not here to like, I have no doubt that given time I can solve all of these puzzles, but I'm more interested in finding unique and novel ways to solve them. So hints just help me keep things going smoothly. So, I mean, my gut reaction, or my gut instinct, is to just make a really long array. Put some nils in it. Keep on going. Yeah. I feel like that's not the most novel solution. Just doing the array thing. We could... Oh, I have an idea. Let's parse it in a really let's yet again parse this in a really silly way. Let's write something like this. Class disk. We're gonna worry about the implementation of that later. And we'll say disk equals disk.new input dot chars dot each do or chars dot map to I. Let's do some more operator shenanigans. We don't have to do that. We can just shovel in each one. That seems good. And that'll build us our thing, and then we'll figure out what the API actually is for this thing. So we do need some state in this object, because we are alternating between file and free space. And we'll initialize our blocks to be an empty array. and our current ID to be, are we starting the IDs at 0 or 1? We are starting IDs at 0. And then we can implement this. We'll say case one, or case mode. In case you wonder why I just typed a capital W instead of a @ symbol, it's not because the keys are next to each other. On my keyboard, they are the same key. File when free space. And then every time we do this, we alternate. So I guess we can put that within the blocks. We'll say the end of each of these, we'll say mode equals free space. Mode equals file. All right. And we'll do @blocks, or what if we do n times @blocks shovel in the ID, and after this we want to increment the ID by 1, and then that makes sense. I think that does what we want. And then here we just do n times shovel in nil. Something like that. Block is supposed to be blocks, and that did not. Oh, this is supposed to be disk.inspect. All right, that doesn't look right. Nope. And this is because I put a 1 there instead of an n. I was like, why? How could they all be exactly 1? Okay, so this looks more like what we expect. Okay. And then we want to disk.compact and then read out disk.checksum. And let's just implement checksum first. Double check what the algorithm is for that. So add up the result of multiplying each of these blocks' position with the ID file number it contains. Okay, so that's pretty easy. In Ruby, @blocks, each with index, .sum, and this is going to take, we're going to have the ID and the index. Wow, I really got to figure out what that bug is. And we multiply them together. So this should work. It won't get us the right. It won't get us the right answer, but right, there's nils. Next 0 if id.nil. I think that's what they said. Block contains free spaces is skipped instead. Yeah, in fact, since we're writing bad code, you know what? Let's make this really obtuse. Let's go _1 ampersand colon asterisk _2. Oh, nil. Oh, so this has got to be or 0. Lovely. Okay. Beautiful. So then let's write our compaction. So we want to iterate backwards. So let's create a I don't know, a file pointer, and we'll set that to blocks.length -1, right? That's yeah. Actually, no, we can index backwards. Oh, but I think it's more useful for us to have an index that's from the beginning, because we're also going to want a blank pointer. Now, does the array index method return the first index of an element we asked for? Returns the index of specified when the argument returns the argument object is given, but no block returns the index of the first element for which object double equals element. Okay. So we want to start at the first nil. And so at each step, we want to say blocks. I think you can pass a negative. Yes, you can pass a negative argument, but I want to know when our blank pointer, when our file pointer and our blank pointer cross, if they do, I think. I'm still not 100% on that, but I think I want to be able to check that to know that I'm done, right? But yes, you can do negative pointer or negative and indexes into arrays. That does work. So we will say blocks. We'll call it blank pointer. Or call it free pointer actually. So free pointer is going to become equal to blocks file pointer, and blocks file pointer is going to be equal to nil. Then we want to move the file pointer backwards until the next non-empty block, and the free pointer forwards until the next empty block. Is there like a do while in Ruby? Oh, yeah, Stack Overflow. He suggests using loop. Okay. Loop do file pointer minus equals 1 break if file pointer, and then we just want to check it at blocks file pointer. And then we want to do basically the same thing for our free pointer, but we're adding one. And we're checking if it's nil. And this will infinite loop, I think, currently. Run it. No, it did not infinite loop. It just gave a totally plausible output. Because we didn't iterate. There's no loop here. This whole thing needs to be in a loop. And then we need to break if free pointer is greater than or equal to file pointer, something like that. Okay, produce a result. Be neat if that just worked. It did. Cool. Day 9, part 1. Okay, let's do part 2. Upon completion, two things immediately become clear. First, the disk definitely has a lot more contiguous free space, just like the amphipod hoped. Second, the computer is running much more slowly. Maybe introducing all of that file system fragmentation was a bad idea. The eager amphipod already has a new plan. Rather than move individual blocks, okay, so this sounds like it's exactly what we expected, he'd like to try compacting the files on his disk by moving whole files instead. This time, attempting to move whole files to the leftmost span of free space blocks that could fit the file. Attempt to move each file exactly once in order of decreasing file ID number, starting with the file with the highest file ID number. If there is no span of free space to the left of a file that is large enough to fit the whole file, the file does not move. The first example from above now proceeds differently. Indeed it does. The process of updating the file system checksum is the same. Now this example's checksum would be 2858. Start over now, compacting the amphipod's hard drive using this new method instead. What is the resulting file system checksum? Okay, so one of the things that's interesting about this one is that, like, realistically what we actually want to store now is the chunks, whether they're chunks of free space or not. And then which makes this trickier. So let's plop some stuff in here. Let's see. What was I going to do? Oh yeah, raise part 1 to S, and last part 1 equals our known correct solution. And then let's do a part 2. We don't need this. And so we'll do the same thing, except we're going to call compact 2. Now I want to refactor this to store this stuff as not as blocks but as chunks. In fact, this is just a data class, right? And so we can do some fun stuff here. It's kind of interesting to re-implement the original compact this way. Is it going to be really annoying? Do I care enough to do it? I guess is the other question. Well, we've committed it. We can start and then see where we get. Maybe it is going to be too annoying. Yeah, I don't know if I really want to do that. Okay, so let's back up. Or let's continue this path. But we're going to just axe part 1. And re-implement it to do the new thing. So each of these we are now adding to the chunks a new chunk with the ID at ID and the size n. And we're doing the same thing for free space, but it's going to be nil. And then this will probably want, oh, I hate that. We are going to, what are we going to do? We are going to define a free space method on this thing. And then we no longer have a file pointer. Oh, sorry, a free pointer. We only have a file pointer. And so let's just remove any references to that. We're now going to say the logic for breaking is now if there are no free spots to the before this index. So for doing that, and you said we've got like 1, 2, say a equals 1, 3, 22, 1, 3, 4, nil, 12. And our index is going to be a.length minus 1. And so slicing a dot slice 0 to I gives us okay. Have we incremented the index at this point? We can do this check before we do this. We can say this is chunks, not blocks. If at chunks dot slice 0 to file pointer. It's all the ones before this one because we've already nilled out this one at this point. Any or none are free space. And then we did this loop. Until we find our next free space one. We could do something else, but I don't know, that's fine. All right. So this is where our actual logic needs to go. And what we need to do is insert. We need to find the first. So we'll say current chunk we're operating on is this one. And we need to say at chunks dot find, and we are looking for a chunk whose size is greater than or equal to the size of the chunk we've got. Actually, we want to find the index, not just find it, right? So index can take a block. That's perfect. Free. Oh, and we only actually want ones that are free space. That could have been a fun bug if we'd missed that. Free space pointer. Okay. And so now we have the free space pointer. That blocks. Indeed. Thank you. And this one is just totally wrong, so we'll have to deal with it later. That's all our blocks, just that one? Cool. All right. So we're going to want to do something like at chunks free space pointer equals what do we call this method? Insert, I don't know, chunk. And that's going to return one or more chunks. And then we need to flatten chunks in case it's returning an array. And so let's go implement insert. So in the case that we're inserting, let's just put raise okay, we can't insert stuff into anything that's not free space. And in the case that the sizes match, that size equals chunk.size, that means it's slotting in perfectly, and we can just return the original chunk. If that's not the case, then we are going to have to return an array that contains the original chunk and the additional free space, which is going to be a new chunk, that, and size dot size minus chunk dot size. That seems right. Now, I mean, if we get to the checksum, let's see if we run this. Do we get as far as the checksum? No, I did the same thing I did last day and forgot to make those symbols. This is slow. And undefined method free space for nil. Interesting. That should never happen. Because we're, oh, that's supposed to be triple, I think. Yeah, perfect. All right, so that gets to the end. It's slow. That's expected. We're doing a bunch of mutation and making new objects and stuff. That's not expected to be fast. So chunks dot flat map. I'm gonna do something silly. I don't know that. And then do that, and then we just have to implement 2a on here. And that is, it's going to be size how would you describe the performance of that? I think I can just use an array constructor. 4-minute running solution. Oof. I mean, yeah, okay. That is slow. All right. Answer is too high. All right, so that's interesting. We have very little visibility into this, which makes it kind of tricky for us to know where the bug might actually be. Make sure that actually does what I want. So array new should be 312s. Yeah, okay, that's what we expect. Doesn't give us a lot of information. Oh, is the checksum still the same? Yeah. How should we debug this? We can always use the original input. Maybe we start with our test input, add visualization. So I guess we can see if that even produces the right results. Whoops. 2772, and it is actually 2858. So let's examine the resulting. Let's implement 2S on this thing. With index, oh, we don't need the index here. We're just mapping them. And these are just IDs. So we're just mapping them through 2S. I don't even know if we need to do that. It'll happen automatically. That only complete files can be moved. I'm realizing that we may be moving files the wrong direction. Because if there's not a spot to move a file, we're not moving that file. We're moving it, or no, I don't think that. We'll have to investigate that. But let's take a look at what the resulting output looks like. Oh, I have to actually print it, don't I? So we get 0099111233. Okay, so let's compare that with 992 has been moved. Okay. File ID 9 is split. What do you mean? It's not split here. It's not split here. Oh, it's still there. That's funny. Why is it still there? Yeah, yeah. Okay, I'm just gonna print it walking through like step by step because I think that's probably useful. That's... Oh, we're not printing the dots. Okay, so let's fix that. Okay. There's the output we're actually looking for. Not correct, but almost correct. So we start here. The problem is the second step. We're not removing the ones from the end, but like, how is that possibly the case? We're setting chunks file pointer to nil here. We could even like that, you'd think would be good enough. Oh, there we go. We're still getting the wrong result because something's algorithmically wrong, but that's fine. So let's step through. 9 moves to the correct position now. That's cool. Then we try to move 8. And 8 erroneously moves by 1. So that's weird. So that's wrong. 8's not supposed to move. So yeah, we're handling an edge case, or we're missing an edge case. Free space pointer. So we only want to do any of this work if free space pointer is less than or equal to, no, less than, what couldn't be equal to, the file pointer, right? Okay, so now, no, we're still moving 8. What the hell? So free space pointer is 1 correctly. The free space pointer is 2. 1, 2, what? Well, no, here. That's not free space. I don't like the compact. It's just to remove the last item. Are you removing free? Oh, interesting. I guess instead of that, we should just put an empty block in its place. We're never going to sit in it. We don't need to, we don't even, okay, so. File pointer. We're getting totally wrong values, which is interesting. Are you removing free space? Well, now we're inserting free space, so 8 doesn't move. So then we try and move 7. And 7 obviously can't go there. What the hell's going on? What the hell? Well, no, because and if they're equal, then the free space we found is the file that we're looking at, which is impossible. I'm just going to print this out and compare this to where we're getting to. So the first step is currently correct. The second step is technically correct. We're not. Yeah, no, that's elsewhere. Because we're not moving the 8s. And then the next step should be to move 7s to here. And it is not. Hey, Marco, how's it going? We are currently stuck on part 2. Just debugging our solution. We're getting output very similar to what? Oh, yeah, of course. Thanks for helping me. Thanks for coming up with such great ideas for the streams. Yeah, so this is the check that you were referring to, Fig, where we check to make sure that we will look for the first free space whose size is greater than or equal to the size of the chunk that we are moving. And I guess I want to put chunk see what's going wrong there. So on our first pass, that's our current state, and we say, yeah, we can move 9 into that spot. This spot. Perfect. We do that. And then we say, uh-oh. What the hell? We're all ID nils from here on out. Oh my god, what? Chunks file pointer. How are we hitting a nil now? So that moved the 9 correctly, and then Ha, okay. Perfect. Um, so now we hit, now there's, we correctly identified that there's not a spot A, and then we get the right answer now. All right. So yeah, so the reason we're using loop here is actually really interesting, and I maybe should have called this out more explicitly when we were looking at the Stack Overflow related to this, is that Ruby doesn't have a built-in do-while loop like some languages have. And Mats has specifically come out against using like begin and then sticking a while on the end of it. So the two move. The two did not move. 2858 is the right answer. Oh, interesting. Uh-oh. We got the right answer, but why didn't the two move? Oh no, we print out before each step. The two did move. That's just because of where the puts is. Good call out though. We do it before each step. But yeah, so if you want to do a do while in Ruby, you kind of have to. Yeah, the last frame didn't print. Good catch though. So this is the best way to do. This is the official Matt says so idiomatic way to do a do while loop is to just have a break at the end of a loop, which is fine, works for me. So if we remove our short circuiting there, it's not fast, but it should produce a result. Fix my window here. Hooray! All right. So in this one, we didn't get too weird. We used a data object. We implemented disk using the shovel operator to add data to it. For part two, we sort of changed the underlying implementation, which allowed us to avoid changing the actual way. Like this code didn't change from part one to part two, which was kind of nice. So we actually got to see, an example of refactoring an object without changing its API, which I don't know. That's not weird. That's just normal. But it's nice to see it work. This is not beautiful, but it works. The naming. Thanks. Yeah. I am pretty happy with the naming side of things. This we showed 2S for debugging things. Yeah. Fingers crossed that maybe day 10 will be evaluable. I'm still holding out hope. We still got plenty of puzzles to go, but we'll see what happens. So tomorrow I will probably not be streaming, and I will probably be back again Wednesday, I would expect. Got a bit of stuff going on this week. And tomorrow it looks like the surf report's going to be really good, so I am going to go surfing. So thanks everyone for coming out, and see you next time.